This is a review of kinematics for AP Physics 1. Kinematics is the study of the motion of objects without considering the causes of that motion. A vector is a quantity that has both magnitude and direction. So when I say magnitude, I'm talking about the size of something. And the way we typically represent the size of a quantity in physics is we have a number and a unit associated with that size or that magnitude. A vector also has direction, which tells me in which direction something points. Sometimes that's indicated with an angle, which is more precise. Sometimes it's indicated as north, south, east, west. And sometimes it's just indicated by whether something is positive or negative. And then a scalar is a quantity that only has a magnitude, which means there's no direction associated with the quantity. It's just how big it is. So there's just going to be a number and a unit. Next, I want to make sure that we have a well-defined understanding of position. The way that we track the positions of objects in physics is we place that object on a coordinate system. A coordinate system, or something like an xy plane that is on the right, has a defined positive x and positive y direction. And then we put the object somewhere on that xy plane, and we can use its x and y coordinates in order to determine where it's at in space. This also helps us understand whether the position is positive or negative in either one of those two directions. Two quantities that are important to understand in kinematics are distance and displacement. Distance is just the length of the path that I travel. So if I start off at some initial position, x initial, and I move to some final position, x final, and I walk along some irregular path in order to get to that final position, then the distance that I've traveled would be the length of all of those segments of that path added up together. So that total distance d could be represented as d1 plus d2 plus all of the segments of that path. The displacement, which is the straight line distance from the initial position to the final position, would be represented by this arrow. It would start at xi and point towards xf, like that. That's the way that it would be represented in this two-dimensional space, in this two-dimensional path that I've drawn. But in any one dimension, in any one direction, the displacement can be found by just subtracting the final position minus the initial position. So if I wanted to find my displacement in the x direction, I would just use whatever this final x position is and my initial x position and subtract. So final minus initial to find the displacement in the x direction. And then in the y direction, I could use my initial y position and my final y position in order to calculate my displacement in the y direction. And ultimately, I could use my displacement in the x direction and my displacement in the y direction to find my total displacement, which maybe here we represent as delta s. Just some arbitrary displacement that depends on my displacement in the x and y directions. So bottom line, displacement is a straight line distance that points from the initial position to the final position. It does not depend on the path that I take, only on those initial and final positions. In one direction, the way that I calculate that is I subtract the initial position from the final position. So xf minus xi. Sometimes the distance you travel and the displacement are the same. So for example, if in the graph that I've drawn, if my initial and final positions are the same as shown, and the path that I walk is along this line, this green line, then my distance traveled and my displacement are exactly equal. But the original case where I had drawn that red line, and then later drew the yellow vector which represented the displacement, in that case, the distance traveled is obviously much greater than the displacement. And so these quantities are not the same. I think that this can be further illustrated Here on the right, I have a little track drawn. And so you might imagine somebody starting off at this initial position here, so x initial, and they go all the way around the track. Maybe they're running in a race, and they return back to the initial position. If this track has a certain distance to it, right? Maybe this is a track that has a total length of 400 meters. Then when the person returns to this starting location, they will have a displacement of 0 because the initial position and the final position would be the same. Their distance traveled, however, would be 400 meters because if the length of the track is 400 meters, the path that they will have traveled by the time they return back to this initial position would still be 400 meters. And so there's another instance where distance and displacement are not the same. While distance and displacement are different, as we've seen, they are both measurements of length. And for that reason, we need to know and remember that the base unit of length is the meter. And so distances and displacements are measured in meters. So if you're going to use a distance or a displacement in a subsequent calculation, it's important that these quantities are measured in meters, but we often, see things measured in centimeters or kilometers, or maybe even in places where you don't need to do very many calculations, miles or something else. I'd also like to point out that distance is a scalar. It only has a magnitude. So distances will be represented by things like 20 meters or, 50 centimeters. It's just the number and the unit that matters. For displacement, not only does the number and the unit matter, but the direction also matters. And that's why every time I drew the displacement in the graph on the bottom left, I drew it as an arrow. And that's because displacement is a vector, and vectors can be represented as arrows, because we're trying to indicate the direction that it points in. So displacement could be, the direction of the displacement could be given by an angle, or it could be given by a north, south, east, west type of direction, but most often displacement directions are just given by whether they're positive or negative. And so imagine something moving in just a straight line along the x-axis. If it's moving to the right, then it has a positive displacement. If it's moving to the left, then it has a negative displacement. And so when I look at the displacement, I should be able to see whether it's positive or negative to determine whether it's moving to the left or to the right. Next, I'd like to talk about speed and velocity, which are related in a very similar way to distance and displacement. That's primarily because the total distance that I travel is going to be used to calculate speed, and the displacement of an object would be used to calculate its velocity. Also similar to distance and displacement, these quantities really are quite similar in the sense that they're both ways of describing the rate of change in position of something. So as time goes on, how quickly am I moving along? How quickly is my location changing? And so the greater amount of distance that I travel in a certain amount of time determines my speed. And since distances are measured in meters and times are measured in seconds, then speed is measured in meters per second. And while average velocity is a quite different quantity, displacement is still measured in meters, time is still measured in seconds, so average velocity is also calculated in meters per second. The reason why these are average speeds and average velocities is, for instance, I'm using a final position and an initial position to calculate my average velocity, and a final time and an initial time. So I don't know exactly what happens in between those two positions, but I do know where I'm at and when I'm at two different locations, and I'm using the difference between those 2 points to calculate an average velocity. For that reason, it very much is an average. Acceleration is the next step up after velocity. So if we go from position to velocity to acceleration. and acceleration is a change in velocity divided by time. So I'd like for you to think of velocity as the rate of change in displacement of an object, and acceleration as the rate of change in the velocity of an object. So the more quickly that my velocity changes, the greater my acceleration. And that's why when I calculate an average acceleration, I use two different points with two different velocities, initial and final, at two different times in order to calculate an average acceleration. If you wanted to know the velocity or the acceleration at a particular point in time, then you wouldn't necessarily use these equations. What you would need is you would need to either use a kinematic equation, or you would need a graph of the object where you could go to a particular point on the graph and find the exact velocity or the exact acceleration. In those kinds of quantities, we would call instantaneous. An instantaneous quantity is, in this instant, what is the velocity or the acceleration. So in cases where we are given enough information to calculate the, velocity or acceleration at a particular moment in time, or cases where we're given a graph and we can, from that graph, determine the instantaneous velocity or acceleration, then we know the velocity or acceleration at a particular moment in time. But when we use these equations, we are calculating average quantities, which means over a large time interval, what is a good approximation of the velocity or the acceleration. The idea of uniformly accelerated motion is extremely important in kinematics. An object is uniformly accelerating if the acceleration is constant. And so there's two ways that the acceleration can be constant. Either the net force acting on an object is constant, which means that the amount of pushing or pulling on an object is constant, which means that there's a constant acceleration that's being caused by those forces. Or the net force acting on an object is zero, in which case there is no acceleration. The acceleration is zero, but that still means that it's constant. In either case, we get uniformly accelerated motion. And if we use the equations from the previous slide, we could derive each of the four equations below. The equations that are on the left, these three equations, are all on the equation sheet in one form or another. And I think that it would be important for you to take out your equation sheet and compare the equations that I wrote to the ones that are on your equation sheet. They're very similar. The only differences are, in a few places, I write delta x instead of final position minus initial position. And I've left off a lot of the subscripts. I left off the subscripts just because I think it's cleaner to think about the positions, and the way the variables are related without having all the subscripts there. But the reason why the subscripts are there, if you notice, on the equation sheet there's going to be lots of x's. And that's because they are reminding us, they're doing us a favor to write in all those x's to tell us that these kinematic equations can only be used for one direction or the other. So I can write a kinematic equation for the x direction or the y direction, but I can't talk about the motion in the x direction and the y direction simultaneously. I can only do one at a time. The fourth equation on the right-hand side is not something that's on the equation sheet, but is something that we should be able to just intuitively know. As long as my acceleration is constant, I should be able to determine the average speed by just taking the initial and final speeds, adding them up, and dividing by 2. These are the equations that are at your disposal for solving kinematics problems, or problems in which kinematics can be used to help find a variable. Make sure that you know that these groupings of variables, so the initial and final position, the initial and final velocity, the acceleration, and time, those four sets of variables are the things that are being related in these equations. And some of these equations have different variables. So for example, the first two equations have time, but the third one does not. I think most often on AP Physics 1 questions, the kinematic equations are used to solve for accelerations, which are then subsequently used in force problems. Lastly, I'd like to point out that because velocity and acceleration and displacement are all vectors, the sign that you put into these equations is extremely important. Sometimes velocities or accelerations will be negative. Sometimes positions will be negative. And that information needs to be conveyed in the equation, especially since these terms have added terms, in which case you put something in as positive instead of negative, you will definitely get the wrong answer. Perhaps the most common example of uniformly accelerated motion is freefall. Freefall is where an object is moving only under the influence of gravity. So this happens when a ball is dropped, but it also happens when I throw a ball into the air. Although the ball is moving upwards, it is freely falling because the only thing that's affecting its motion, other than the initial throw, is the pull of gravity. And so here I have an object which at time t equals 0 is at position x equals 0 and has a velocity of v equals 0, which means it's going to be dropped from rest. If I check back 1 second later at t equals 1, the object will have traveled 4.9 meters and its speed will be 9.8 meters per second. The reason why I know that is because at t equals 1 second, the speed must be 9.8 meters per second because the acceleration due to gravity on Earth, which is represented by a lowercase letter g, is negative 9.8 meters per second squared. If the acceleration that falling objects experiences is 9.8, that means the change in velocity every second is 9.8. So an object that starts off at 0, 1 second later will have a speed of 9.8. Its speed after 2 seconds should be 9.8 plus 9.8, or 19.6. And its speed after every subsequent second will just be 9.8 added on to the previous speed in the previous second. And so you should see that after each second, the speed goes up by a linear amount. And what that tells me is that there is a linear relationship between the velocity and time. The position is not linearly related to time in that kind of a way. You can see with this equation on the right that the position and time has a squared relationship. And for that reason, it's not as simple to calculate what that displacement would be, but one way would be to say freefall is an example of uniformly accelerated motion. I can use the kinematic equations from the previous slide. And here that means if I recognize that the initial velocity is 0, that term goes away, and the displacement can be calculated by simply 1/2 a t squared. And since a is equal to 9.8 meters per second squared, then I can just plug in 1 second or 2 seconds or 3 seconds for the time to calculate that displacement. Another way to analyze this motion would be to, instead of use the equation to calculate it, I could rely more on my intuition of the problem. And so let's look at this first interval of time here. I know that I start off at 0 speed and I end up at 9.8 meters per second. At every instant in time, my speed is increasing. However, since I'm traveling for 1 second, I could instead figure out the displacement by thinking about the problem as if I was traveling at my average speed the whole time. So instead of my speed increasing from 0 to 9.8, what if I was traveling at the average speed that I was traveling at the whole time? Well, since I start off at 0 and I end up at 9.8, my average speed would be half of 9.8. which is 4.5, or sorry, not 4.5, 4.9 meters per second. And so if I travel at a speed of 4.9 meters per second for 1 second, I will have traveled 4.9 meters. And so you either use the equation to calculate it exactly, or you use the fact that the acceleration is constant to calculate an average speed, which then could be used to calculate the displacement. More practically, objects are typically thrown not only up or down, but from left to right. Anytime you throw an object, and after throwing it or kicking it or whatever, it's in the air subject to only the influence of gravity, it's not just in free fall, but we call that a projectile. And we can study the projectile motion of an object as it has a trajectory that has a parabolic path, like in the picture that I've drawn. And I want to point out some key things about the motion of these objects. First, I must analyze the horizontal and vertical components of the object's motion independently. I can't work with motion in the x and y directions at the same time. And so, for example, if an object is launched at an angle like it's shown here, then you would need to break that velocity down into its constituent x and y components, right? So you might remember finding the x and y components to vectors. And we do that with all sorts of vectors, but here is especially important. And once you have that broken down, you can start to talk about what's happening in the horizontal and vertical directions. In the horizontal direction, so moving from left to right, which I've indicated in my coordinate system, the positive x direction is to the right. The acceleration in that direction is 0. And that's because the moment I get done kicking or throwing or whatever, launching this object, there's nothing in the x direction that can accelerate it. The only thing that could do that would be air resistance, which is negligible in most cases. And so for that reason, the acceleration will be 0. Now the acceleration in the y direction is not 0, it's 9.8, because at all moments in time, there is an acceleration that points downward. So whether the object is here or here at the very top, right before it hits the ground, or even right as it's being launched, at all moments in time, there is an acceleration in the y direction that points downward of 9.8 meters per second squared. And these accelerations have implications in each direction. So for the x direction, one of the most critical things that we learned in kinematics was that because that x acceleration is equal to 0, by definition there cannot be a change in the velocity of the object in that direction. And so the velocity in the x direction is always constant. If you are given the initial velocity in the x direction, the velocity at this point, then you know the velocity at this point or this point in the x direction because it never changes. Therefore, I would not use one of my uniformly accelerated motion equations to figure out anything about the speed. The acceleration would be 0, and so it wouldn't be, useful for us to apply any of those equations for the x direction. For the y direction, however, the velocity is changing. At all moments in time, this acceleration of 9.8 changes my velocity. And so in the y direction, it's especially important that you incorporate that acceleration when you're calculating a quantity by using those uniformly accelerated motion equations. What I'd like to do now is I want to take the image from above where an object is launched from a certain height, moves to the right and upwards, and then falls back down to that same original height. That example of projectile motion. I want to take that example of projectile motion and I want to make graphs of just about every quantity that we can as a function of time. Let's think about what these graphs would look like. I'm going to do these in kind of a haphazard order. The first one that I'd like to do is the accelerations. The acceleration in the x direction is 0. There's nothing that speeds up or slows down the object in the x direction. For that reason, the acceleration at all moments in time will be 0. In the y direction, there is an acceleration, and regardless of the problem that I'm solving, I not only know what the shape of that graph looks like, but I know what the exact value is down here. That is negative 9.8 meters per second squared for the acceleration. If I take an object, and like in the previous picture, I launch it at some angle above the x-axis, above the ground, so it's moving up and to the right, then the initial velocity in the x direction is positive. For that reason, I should start off my velocity in the x direction graph at some positive number, and it should stay constant. Right? The acceleration is 0, therefore I must have a graph that has a constant slope. And the reason for that is the slope, right, the v versus t slope gives or is acceleration. And so if my acceleration is a constant value of 0, this line better have a slope that has a constant value of 0. Now for the y direction. My acceleration is negative 9.8 meters per second squared, so the velocity better be changing. If I launch an object up and to the right, like it was in the previous picture, then the initial velocity in the y direction is also positive. However, I know eventually the object moves all the way up to its highest point, it stops, and then it comes back down, so then it starts moving in the negative direction. I also know that the slope of this line has to be negative 9.8. And so the slope of this line might look something like this, where the slope is negative 9.8, which gives the acceleration. And the point where the object reaches its highest point, the place where it stops, would be this point here, because that's a velocity of 0, right? Because it's right there on the time axis. And so everywhere above that, the velocity was positive, and everywhere after that, the velocity is negative. So that point, although it doesn't look like it, that point on the time axis is where the object is turning around. Also, as long as the object is launched from the same height that it lands at, so let's say it's launched from the ground and it hits the ground, then that means the net displacement in the y direction is 0. And if you remember, the displacement, okay, is given by, for a velocity versus time graph, is given by the area under the curve. So the displacement is the area under the curve, which is the way that we typically say it, the area under the curve, but what I mean physically is everything between the graph, the red line that I've drawn, and the time axis. So that would look like the following: this blue area and this blue area. And if I've drawn my graph correctly, then since the object is launched from and lands at the same height, then the net displacement in the y direction should be 0, which means this positive area above the time axis and this negative area below the time axis should give me a net displacement of 0. For the x direction, that's not true, right? The area is still the displacement, but there's some positive displacement here that I could calculate by looking at the area under the curve. And that should make sense because although the object starts and stops in the vertical direction in the same spot, it certainly does not land in the same spot if it was launched to the right at some angle. And lastly, let's look at the positions. For the x position, we know that the object starts off, let's say, at a position of x equals 0. And we'll say that it starts off at y equals 0 as well. So we're basically centering the origin of our coordinate system on the object where it's being launched from. The x position steadily increases and becomes more and more positive. I know that because at all moments in time the projectile is moving to the right. And so the graph of the x position as a function of time might look something like this, where the x versus t, the position versus time graph, the slope of that graph gives the velocity. So I don't know what the velocity is because this is a generic problem, but the slope of this graph would tell me what the velocity is, and that velocity should be equal to the graph that I've drawn in the one below it. For the y position as a function of time, I know that in the vertical direction the object starts off as 0, it goes all the way up to some maximum value, and then drops back down to 0. So the graph should very much be parabolic like this. And you can see that I've aligned these graphs intentionally, where the object reaches its highest point at that velocity where it crosses the time axis. And even though it's at that highest point, and even though the velocity is 0, we still have an acceleration that is equal to negative 9.8 meters per second squared. If that weren't the case, then the object would stay stuck in the air. That acceleration has to act on the object at all moments in time. And so the slope of these position versus time graphs tell us about the velocity. The slope of the velocity versus time graphs tell us about the acceleration. The area under the velocity versus time graphs give us the displacement. And something that's not as important but sometimes shows up, the area under an acceleration versus time graph tells us the change in velocity. So if I found the area under this graph here, I would know the change in velocity of the object. I would not necessarily know what the initial velocity and the final velocity were, but I could at least figure out by how much the velocity changes. Similarly, if you look at the acceleration versus time graph for the horizontal direction, there is no area under that curve, and that makes sense because the velocity is not changing. And so lastly, I'll add that the change in velocity is the area under the curve for the acceleration versus time graphs. So you should be able to, for a simple case of projectile motion, be able to make all of these graphs. The most important things that I think are useful for making the graphs is trying to decide where does it start and in which direction does it go from there. But please remember what the slope means and what the area under the curve means in each case. A couple other things that are very important to remember is that a lot of times when we solve a problem, it's not the same case of projectile motion every time, right? Sometimes an object might be launched from a table or from the top of a building where it may or may not be launched horizontally. If something is launched horizontally like this, then the initial velocity in the y direction is 0. This is a critical piece of information that a lot of times we forget about. The velocity in the y direction of this object is 0, but the velocity in the x direction is not. Also, earlier in the video I mentioned breaking down a vector into its x and y components. And what I mean by that is sometimes information is given to us in a way that sounds something like this. An object is launched with an initial velocity of 12 meters per second at 30 degrees. So you're given information about the total velocity and the angle, but you know nothing about what's happening in the x and y directions. And so you need to construct a triangle like this and relate the sides of the triangle and the angles to one another, so that way you know what Vx and Vy is, because you cannot plug that total velocity into any of your equations. And so there are actually 4 equations that are important when we start to break down vectors into their components, or when we start to take the components of a vector and build them up to talk about the total quantity. First, Pythagorean's theorem relates to 3 sides. Each side squared, added up, and then square rooted gives us the hypotenuse. The angle that I've drawn there in that triangle is given by the inverse tangent of the vertical component of the velocity divided by the horizontal component. And either the x or y components can be determined using SOHCAHTOA, right? The sine and cosine parts of the triangle. So make sure that you remember these, because these are things that are not only important for finding velocities or accelerations, they're incredibly important in almost every single unit that we've worked in this school year.